percentage of how far around it?
You're in the
You
ballpark
take
there.
the circumference and then divide that by the radian, the angle over 2 pi.
So I think we're going
As in the
back door that
percentage
way.
of the,
Alright, so the circumference of the whole thing is 2 pi r.
and then multiply that by the radius over, or no, multiply that by the angle over 2 pi.
So times the angle over 2 pi.
And then I guess that would, so it'd just be the radius times the angle,
Is equal to what?
the arc length.
Yeah,
That's the relationship there.
I basically took the circumference and multiplied it by the percentage of the full circle that the angle is.
Yeah, okay.
Is that right?
Yeah, that is right. Going at it more of a forward, what I view as a forward direction, is that if I take this radius, imagine I got a piece of string that's the length of the radius, I put it one in here and I start wrapping it around, that's how far it's gonna go, that is 1 radian. If S is equal to, so if the arc length is equal to the radius, that's 1 radian,
and so then it's a question of, well, how many radiuses can it go around the circle? Well, that's 2 pi, so there's 2 pi radians. All right, so we have S is equal to r theta.
I know that my arc length is equal to r times theta, which in this particular case is r times 2 phi. And that's equal to Vt.
Mr. Flux, is your recording supposed to be red on the recording button?
That's blinking right there,
Oh.
so I'm good to go.
Okay.
Yeah, if that were red, then it wasn't recording anything.
Gotcha.
But thanks for checking. So therefore, 2 phi divided by t is just v over r. Bring r over to this side, t over to that side. I just happen to have 2 phi over t right here. So it's negative 2 phi over t times v, j hat, which is negative v over r times v, j hat, which is negative v squared over r j hat. So if I have something traveling in a circle at a constant speed, magnitude of the acceleration is v squared over r, and the direction, well, I did it specifically at this point right here, so negative j hat is pointing towards the center, or in general, it's pointing towards the center. So this acceleration, make it slightly more generic, negative v squared over r hat. Now when we dealt with I hat and j hat, we had specific directions. I hat was, we would define I hat and j hat. R hat is a little bit of a special unit vector in the fact that the only thing we have to define with R hat is the center. R hat is a unit vector away from the center. Negative r hat would be pointing, equals points toward the center. So r hat's away from the center, negative is the other direction, towards the center.
So functionally, would this be like, let's say that I'm using a slingshot, would this be the tension on the slingshot?
Mass times this would be the tension on this.
Okay.
Now, turns out how much reality we want to take into it, but close
Right.
enough for war.
Ideal slingshot.
This, of course, has a special name. Anyone want to just shout out what the type of acceleration this is?
Centripetal?
Yep. So let's talk about the vocab there. This is centripetal acceleration. Okay, two parts here. Century, hopefully you can take the leap, and that basically comes from, I think that's the Greek for center. It's not the Greek, it's the Latin. PET. We have other words that use this basic root. That has the same thing, like competition. That PET and competition has the same meaning here.
Opposing?
Seeking. In a competition, you have two groups that are seeking each other. So centripetal means center seeking. It is pointing towards the center. There's that other word, which can be used correctly, but often isn't. And the other word is centrifugal or centrifugal. Depends on how you were raised. Well, let's think about what that means. Still center. What words do we have in English with the FUG, which means basically fleeing?
Fugitive?
Yep. This is center fleeing. This points away from the center. The other one points towards the center. Potentially, this is the last time we use this word in class. There are times for every force, there's an equal and opposite force. So if I'm slinging something around on a string, there's the centripetal force acting on the ball or whatever I'm slinging around. There would be that's a centripetal force acting on that, a centrifugal force acting on the string because it's pointing outwards. Actually, there's a centripetal force also acting on the string. And it also shows up when you deal with rotating reference frames. So if I were slinging something around on the ball, if we tried to do the physics from the ball's point of view, that's the point which also centrifugal force comes into it. Some textbooks will label it as a false force or a pseudo force. It's the illusion in that case of being thrown outwards. Any of you play corners in a car when you're with your siblings, going around a corner and you over-exaggerate the lean? I guess just our family. When you're going around a curve, does it feel like you're being thrown outwards? That is a false force, because what actually is happening to you?
You're continuing straight.
And so as you go around the curve, you want to go that way. So if you're in the car, it feels like you're being thrown to the outside, but it's actually the car is keeping you on the curve. Quoting Godfather 3, every time you try to get out, it just pulls you back in. And I know that was horrible, Pacino. But I went for it anyway. And if you haven't seen Godfather 3, well, if you haven't seen any of the Godfathers, I recommend that you watch them. It's all about family values. Questions?
Can I get a picture of that real quick? I heard that Coda, the re-edit of the third film, is much better than the original cut.
Ah,
I always have people tell me don't watch the third one, just.
I know it got panned, but, you know, it's not as good as the first two.
Yeah.
And I think that's one of the reasons why it got panned. But if you look at it in the scheme of movies, I don't think it's that bad. I think poor casting choice of putting his daughter in the film. But
Yeah.
I suspect Sofia Coppola will find much more success as a director than an actress.
Hopefully.
All right, so why don't we actually, I'm gonna pause this, you can go stretch your legs. Take a small little break here. The videos are still controversial. I had one video banned in 4 countries.
Wow.
I can only guess why, I'm not 100% sure. You know, physics, it's only cutting edge.
Was your example like the tank is rolling down the streets of Tiananmen Square?
I think it's the one, I was showing Tacoma Narrows bridge disaster, and I suspect it has something to do with that, but I'm not told why, all I'm told is it's banned in like, Pakistan.
You're the bad boy of physics.
That's right, hey. Trying to remember, have we done what this means in terms of direction? What the X versus the dot means? We did that. When you're we're now gonna be dealing with multiple dimensions here. And so this is to indicate that this is a car on a road and it's driving away from us. And the memory trick is, if you think about an arrow, if an arrow is coming at you, you see a point. And so that, a dot right there, would indicate out of the board or toward the viewer. Out of the board. And if you see the arrows going away from you, you would see the feathers. And yes, I know feathers on an arrow are not crossed like that, but it's the memory trick. That would be into the board or away from you. If you get your own memory trick, great. It's just, I'm sharing the one that worked for me. So this is from the back end rear view. From an overhead view, I have a car that's traveling at some speed V. It will be traveling at a constant speed. So the magnitude of V, constant. And it's traveling in a circle. We assume that it is not sliding. Obviously, if you've ever taken a turn too fast, you hear that screech as the tire rubs against the road. We're not doing that yet. So, I want to find the maximum speed so such that car does not slide. Get that on the meters. Assuming typical, this is car tire, rubber, like it's asphalt. I'm going off of memory on this one. Use of S is at somewhere around 0.8. Use of K is somewhere around 0.7. General ballpark.
All right. We'll go through the exact same process as we've done before. What's the first thing we do?
Label our forces.
Since the car is the only thing I really care about, let's just. What are the forces acting on the car?
Wait.
Friction
Going which way?
towards the center of the circle.
If those are the only forces, that car is accelerating down like that.
Normal forces?
Yes, I hope so.
We are assuming there's no sinkhole or anything like that involved. All right, so or a Thelma and Louise thing. All right, so we got the three forces here. It is not an equilibrium. There's no way I can add these three forces together to get zero. But it's traveling in a circle, so I know that it can't be an equilibrium because the velocity will change direction. All right, next, what is the direction of acceleration?
It's accelerating away from the center of the circle. Towards.
Yeah, that's the whole point of the acceleration is towards the center.
Right.
So my acceleration is in that direction. That's the direction of my acceleration. So let's set up a coordinate system. I recommend one in the direction of acceleration and the other one perpendicular, up or down.
Up.
All right. Do we need to decompose anything? Is there any force that is not parallel, anti-parallel, or perpendicular to my vectors, my unit vectors here?
No.
All right, so equations of motion. So I'll have an I hat equation, and I'll have a J hat equation. What is the I hat equation? Or J hat, just somebody, shoot, go for it. Give me one of them.
Normal minus weight equals the mass times 0. It's on flat ground.
All right, one down. Patrick got the easy one out of the way. I believe what he was saying to the rest of you is now he's giving you all the rest of you an opportunity to show off.
Force.
What was that?
Force.
You said force? This one? Or specifically friction?
Oh, for yeah, friction. That's really all I got. What I see.
All right, as a group, what comes next?
Minus the weight.
Weight is going down. We're just dealing with the horizontal right now.
Is it the acceleration?
Pardon?
Is the acceleration?
The acceleration's coming up soon, but equals.
Yeah.
Equals what?
Acceleration.
Times mass.
There we go. Yeah, mate. Again, we're just plugging into the forces on the left-hand side, mass times acceleration on the right. All right, this looks like it could be so many other type problems, but we now get into the more specifics, the substitution phase. Are there any equation, do we have an equation for anything here that is independent of this problem?
Weight.
All right, what's the formula for weight?
Mass times acceleration.
You could just stay mg and cut out the rest of the language. All right, so w equals mg. All right, so we got something for that. Do we have any other, do we have an equation for anything else?
Would the friction be UK?
All right, so which friction is it? Are we dealing with static or kinetic? Are the tires sliding against the road?
No. So it'd be
Static.
S, US.
Now, the formula for static friction is that it's less than or equal to mu sy. That's the generic formula, but we have this inequality here we have to somehow deal with. Which is why when you're dealing with a problem like this, generally it's given at extremes. I'm trying to find the maximum speed such that the car does not slide. So I'm dealing with a maximum static. And we've got one more. And this one I'll sort of spoil for you. Unless somebody want to go for it? Because this is centripetal acceleration involved here. We have the vehicle is traveling in a circle, centripetal acceleration is involved. This A here, this A is centripetal acceleration. And the formula for centripetal acceleration is the one that we just derived, E squared over R. And so we will plot these into the equation. So now I have mu sy is equal to mv squared over r. And I have y is equal to mg. So we have three things to substitute there. At this point, it's a question of how you want to solve it. I'm trying to find